So continuing on, we're looking at writing out the isotope symbol for the following chemical species and the following ion. So we know that the number of protons is equal to the number of electrons minus the charge. So in this case, we can solve that we know we have 54 electrons and we have a charge of +2. That in turn gives us 52 protons. We also know that our mass number is equal to our number of protons plus the number of neutrons, which is equal to 52 plus 72, or 124. So would someone like to help me out?
128.
Wait, sorry, what? Could you repeat that?
Oh, sorry. You suppose. Oh, sorry. Never mind.
Oh, okay. I was worried I made a calculation error. Okay, yeah. So now that we have the mass number, if we're looking up the atomic symbol, what element has 52 protons? What element has 52?
Hey, Professor.
Is it thallium?
Yep, exactly right. Yes, how can
Professor, I think a proton is supposed to be 56.
Ah, yeah, so I see. So the number of protons, number of electrons, plus the charge. Sorry, I was using the wrong equation. Yeah, this should be 56. Yeah.
Professor, what's the number on the bottom where it says mass number is 52 plus what?
In this case, it would be after we revise our protons, it would be 56 plus 72. And that in turn would give us a mass number of 128. So let's just adjust that really quickly. So then looking up in the periodic table, what element has an atomic number of 56?
Barium.
Yep, exactly right. So this would be barium, 128 over 56, 2 plus. So we'd fill in our symbol, we'd write out our mass number and our atomic number, and then place the charge. Does that make sense to everyone?
Yes.
Any questions on this example? So let's keep going now. And in this case, we are looking at assuming that we have an ion with a -1 charge. We know that our number of protons is equal to 9. So that, oh, sorry, one moment. Let me clear that. Don't know our number of protons is equal to 9 just yet. Let's show where we got that from. So we know that our number of electrons is equal to 10. So our number of protons is equal to our number of electrons plus the charge, which is equal to 10 minus 1, which gives us 9 protons. Our number of neutrons is equal to 9. So we can solve for our mass number by adding up our protons and our neutrons. And that gives us a mass number of 18. What element in the periodic table has an atomic number of 9?
Fluorine.
Yep, exactly right. So this would be fluorine, 18 over 9 minus or -1, however you prefer to write it. Does that make sense to everyone? Does this example make sense? Any questions I can address on this example before we move on to the next example? So let's clear this drawing. And if you have any questions, of course, don't be shy to ask them in the chat or verbally. So in this case, we're now asked to determine whether the following species are ions, isotopes, allotropes, or different elements. So magnesium and magnesium 2+. So what do we think? What do we think? So we have magnesium and magnesium 2+. Are those isotopes, ions, allotropes, or different elements?
Isotope.
Ions.
They would be ions because they're the same species except with a different charge.
Oh, that's right. That's right.
Does that make sense?
Yes.
Perfect. May I clear this example? Okay. So let's look at these next two, as these are a little more tricky. So we have the isotope notation, and we have the symbols, the atomic numbers, which are down here. So these numbers here are our atomic numbers, while the numbers up here are the mass numbers. So what number is different, the atomic number or the mass number?
Mass number.
The mass number. So what do we call two different atoms with different mass numbers of the same?
Isotope.
These would be isotopes because they're the same element and they have different mass numbers.
What about the allotropes?
Allotrope describes two chemical species of the same element with a different chemical formula. It's a definition that applies primarily to elements and different formulas of the same element. It's just a distractor term in this case. It just is making sure that students know the definitions when they're picking a choice from this list. Does that make sense?
Yes.
Perfect. So let's look at this next case. We have cobalt 59 2+ and cobalt 61. So what are these species? And you can check multiple boxes here.
Ions.
Yep, they're
Isotopes.
ions, and they're also isotopes. Does that idea make sense?
Can you explain that just a little bit further?
Yes. So first and foremost, we see that our mass numbers are different. So first and foremost, we have different mass numbers for the same element. And we have the same element. Additionally, these two species each have a different charge. So we can conclude first that they're isotopes. They're two atoms of the same element with a different mass number. And because they have a different charge, we can consider these species ions, where cobalt 2+ is the ion of neutral cobalt. Does that make sense?
Yes, thank you.
Perfect. So let's keep going on this example. And now we're doing some isotope abundance analysis. So an element has two naturally occurring isotopes. In this case, we're going to have to pull up a whiteboard to discuss this example. So let's copy this. And let's pull up a whiteboard in OneNote. So let's copy over a few of the questions. And then let's discuss this example. So let me share my screen. So first and foremost, we're given an element has two naturally occurring isotopes. Isotope 1 has a given mass and an abundance of 57.4%. Isotope 2 has the following given mass. and we're asked to find the percent abundance of the second isotope. We know that the percent abundance of isotope 1 plus the percent abundance of isotope 2 must add up to 100%. If we add up all of our isotopes, the total abundance is 100%. Does that make sense?
Yeah.
Okay, perfect. So then, from here, we know that we can solve for the percent abundance of isotope 2 by taking 100% minus the percent abundance of isotope 1. So we have 100 minus 57.4%, which in turn gives us 42.6%. Does that make sense to everyone?
Yeah.
Okay. So now that we have this information, so I'll make sure to get this corrected in the final version, but moving on from here, let's carry through this example and let's try to calculate the atomic mass of our element. Given the masses and the percent abundances, we can calculate our atomic mass. So our average atomic mass in this case is equal to the percent abundance of isotope 1 times the mass of isotope 1 over 100 plus the percent abundance of isotope 2 times the mass of isotope 2. And if we calculate our average atomic mass for our compound, we get our first percent abundance of 57.4% over 100 times our first mass, which isotope 1 has a mass of 120.9038. So we have 120.9038 plus the percent abundance of isotope 2 over 100 times the mass of isotope 2, which is 122.9042. So then, if we punch this into our calculator, punch that into our calculator really quickly. That gives us let's punch that into our calculator. That gives us an average mass after calculation of 121.7560 AMU. And would someone like to tell me, after rounding, since our percentages have 3 sig figs, we can round this in turn to 122 AMU. What element in the periodic table has an atomic mass of about 122 AMU? What element in the periodic table has this atomic mass?
Antimony?
Yep, exactly right. So that would be the symbol. Does that make sense to everyone? Does this look familiar to everyone? We covered this in chapter 2. Any
Professor,
questions?
what's the point to divide 100? Is it supposed to be 100%?
Yes, but we have to convert our percentages into a decimal. in order for this percentage to be used to calculate a weighted average. If we didn't divide by 100, we would get masses that are 100 times too large. Essentially, this percentage can be used to calculate a weighted average if you convert the percentage into a decimal. Does that make sense? Did that?
So you just divide by 100?
And that allows you to use the percentage to calculate the weighted average of your atomic masses.
I didn't divide by 100. I just use the percentage time and calculate.
Oh, then that would work fine. In that case, your calculator is automatically dividing by 100 when you use the percentage function.
Okay.
But that's more than okay. I'm just showing you in this written form how you would enter this into your calculator if you weren't using a percentage function. Does this example make sense?
Yes, thank you.
Perfect. So continuing on, let's answer this really important question. If you sampled a single atom of that element, would the mass of that element match the atomic mass found in the periodic table? What do we think?
No, but I don't know why.
It wouldn't, because if we think about the atomic mass in the periodic table, so if we think about the atomic mass in the periodic table for something like antimony, which is 22, this atomic mass, by definition, is the average atomic mass, right? And because it's the average of all of our isotopes, the average by definition will not match any of the component isotope masses. Does that make sense?
Yes.
Perfect. Any questions on this idea, on this concept?
No, but Professor, for number 31, did we skip that on purpose or?
We did that already. We wrote the symbol.
That one is okay, the antimony. Okay.
Yeah.
I got confused there. Sorry.
Yeah, no problem. Any other questions on this set? Let's look at question 33. This, if you've done the lab, this one should be pretty familiar. So a student measures the mass of 10 identical metal pieces and they attempt to measure the volume. The pictures shown show the graduated cylinder containing water before and after addition of the metal pieces. So let's write the initial volume in the graduated cylinder. So we're looking at our before column. Okay, so first we need to figure out the value of a tick. And as you see, in 1 milliliter, it takes us 10 ticks. So then we can report up to 1/10 of a tick. So let's figure out the value of 1 tick. So we know 1 tick is equal to 1/10 of a mil. And we can report up to 1/10 of a tick, which is equal to 1/100th of a mil. In other words, 0.01 milliliters. So now reading from the bottom of our meniscus, let's record a mass value. So reading from the bottom of our meniscus, so it looks like we're at about 8.80 milliliters. What does everyone think? Does that value make sense? Does everyone see where I got 8.80 from? We are 2 ticks down below 9, and the bottom of our meniscus is almost right on the line. So I'd estimate our volume to be about 8.80 milliliters. We can report and estimate up to 1/10 of a tick, and that's why I reported this value up to 1/10 of a tick. Does that make sense?
Yes.
Does everyone agree with my volume assignment? Does this make sense to everyone where I'm getting these numbers from?
Yes.
Okay, perfect. So let's look at the next part of this question. And we're asked to report the final volume of liquid in the graduated cylinder. So we already know, and we can leverage the fact that we know that 1/10 of a tick is 0.01 mils. So we see that we're 1, 2, 3, 4, 5, we're about 6 ticks up. So I'd estimate this to be about 10.67 milliliters. Does that assignment seem reasonable to everyone?
Yes, but when I type 10.69, it just keep repeating 9.
Oh, I have never seen that error in Canvas. As long as it's within the estimated digit range, you'll receive credit in Canvas.
What was the issue?
I'm not actually, it appears that if your number ends in 9, Canvas just repeats the 9 continuously. I've never seen that.
Not just that, I entered 8.0 and then computer automatically write as 8.00007.
Oh, I've never seen, Canvas should mark that correctly. I've never seen that error before. I'm not sure. As long as you're within the estimated digit variation, you'll receive full credit for this question. Because this question has been designed that if you round following significant figure rules, your answers will be within the acceptable range. If you don't follow significant figure rules, I've set up the question so that the final answer will not match the target range. So, continuing on, now that we have our initial and final volume measurements, so we have our initial volume of 8.80 milliliters and our final volume of 10.67 milliliters, we know that the volume of solid is equal to V final minus V initial. In other words, 10.67 minus 8.80. So punching that into our calculator, remembering that our answer should have the same number of decimal places as the number with the least number of decimal places, we get a volume of solid of 1.87 milliliters. Does that make sense to everyone?
Yes.
Any questions on this example? If not, let's keep going now and let's figure out the mass. So let's look at the data that we're given. So the initial mass of an empty beaker was found to be 13.03 grams. The mass of our beaker plus our solid was found to be 29.94 grams. So we can figure out the mass of our solid via difference. So we take the mass of our solid and our beaker and we subtract the mass of our empty beaker. That in turn gives us 16.91 grams. Does that make sense? How we calculated the mass of our sample by difference? Does anyone have any questions on this example? Any questions? So let's keep going then. And let's look at the next part of this problem. So the student measured the mass and volume. So remember, we knew that our mass was 16.91 grams, and our volume from the earlier problems was found to be 1.87 milliliters. Since density is defined as mass over volume, we take our mass of 16.91 grams over our volume of 1.87 milliliters, and that in turn gives us 9.04 gram per mil as our final density. Does this make sense? Does this example look familiar to everyone from the laboratory? What does everyone think?
Yeah, I remember.
Okay, perfect, perfect. Okay, so let's keep going now. So now that we know our sample density, we're asked to figure out what is the mass of a sample in grams of the unknown solid that has a total volume of 2 liters. So what I'm going to do is I'm going to copy this question into OneNote, so that way we can have a little bit more of a productive discussion and use a little bit more space. So let's share the OneNote screen for these next 2 questions. So then, given that our sample density is 9.04 gram per mil, we're asked to go from a volume of 2.0 liters to the mass of our sample in grams. So I'm going to convert my volume into milliliters and then use my density to convert to grams. So if I have 2.0 liters, I know in 1 milliliter, I have 10 to the negative third liter. Additionally, from my density, I know I have 9.04 grams of sample for every 1 milliliter of sample. So that in turn gives us 2.0 times 1,000 times 9.04, and that gives us a final mass of 18,080 grams that we round to 18,100. Sorry, not 18,100, that we just round to 18,000 because our final answer needs to have 2 sig figs because our input had 2 sig figs. Does that make sense? Does this example make sense?
Yeah.
Perfect, perfect. So let's look at the next part and variant of this question. We're asked what mass of aluminum, which has a density of 2.7 gram per mil, would have the same volume as 1.9 grams of the unknown solid. So I have 1.9 grams of my unknown, and I'm asked to convert this into a mass of aluminum. So to do this, I'm going to calculate the volume of my unknown in this 1.9 grams using the density of my unknown, and then I'm going to use the density of aluminum to convert the volume into a mass of aluminum. So then I take 1.9 grams of sample, and I know that in 1 milliliter of my unknown, I have 9.04 grams. And then I know for aluminum, I have 2.7 grams of aluminum per 1 milliliter. So punching this into my calculator, 1.9 over 9.04 times 2.7, and that gives us a mass of 0.567 grams, which we round to 0.57 grams. Does this make sense? Does this problem make sense? Does this type of density calculation look familiar to everyone?
Professor, is that number 38 or 39?
This one is number 39.
Okay.
Number
thank you.
38 was done up here.
Right. Okay. Thank you.
Any other questions that I can address?
Number 37.
If your density is a little bit different, that's okay.
Okay.
That's more than okay. Do these examples make sense? Do these calculations make sense? So let's keep going now, and let's look at the main screen. And let's look now at question 40, which I'll copy over, as it's another question that we'll have to address more quantitatively. So in this case, we're asked to calculate the volume in cubic centimeters of a block with the following dimensions. Okay, we need to make sure that our answer follows sig fig rules, and so we'll treat this as 3 separate unit conversions. So I'm converting 50 millimeters to centimeters. 2 centimeters can stay exactly as is, and I'm converting 0.0400 meters into centimeters. So now that I have my problem map set up, let's execute on my unit conversions. So to go from millimeters to meters, I know I have 10 to the negative third meter per millimeter. And then to go from meter to centimeter, I put centimeters on top, and I have 1 centimeter per 10 to the negative second meter. That in turn gives us 5.000 centimeters after this conversion, respecting the fact that our initial answer had 4 sig figs, so our final answer must have 4 sig figs. Does this make sense? Does that unit conversion logic make sense? Is everyone comfortable with this idea? Any questions?
So that was just converting
The 50 millimeters into centimeters. It's just one part of this problem.
Okay, yeah.
So we're not quite done, but I just want to make sure everyone's comfortable with the first step. Okay, so let's keep going now. We're converting 0.0400 meters to centimeters. And we know that in 1 centimeter, we have 10 to the negative second meter. And that in turn gives us 4.00 centimeters. So now that I have all of my lengths in centimeters, my volume is just going to be each of our lengths times width times height. So we have 5.000 centimeters times 4.00 centimeters times 2.00 centimeters. So our final answer needs to have 3 sig figs. And that in turn gives us 40.0 centimeters cubed. Does this answer make sense? Does this question make sense to everyone?
I can only write as 40, but then let me write as
Yep,
40.
that's okay. The problem is set up where if you didn't follow the sig fig rules, your answer would be incorrectly rounded.
And that one is still for number 40, correct?
Yep. This is the complete answer for number 40.
Okay, thank you.
Does that make sense? Okay, so let's keep going now. We're asked to carry out a percent error calculation given the following values. So let's look at 41. So we're asked to calculate percent error, where percent error is equal to the known, well, it's equal to the experimental minus the literature over the literature value times 100%. So plugging in our percent error calculation, our experimental mass is 2.3057 grams. Our literature mass is 2.4506 grams. So this problem is testing your ability to perform multi-step calculations following significant figure rules. So looking at our first operation, which is subtraction, we see both of our numbers have 4 decimal places. So our answer should have 4 decimal places. So that in turn gives us a preliminary value. So 2.4506 minus 2.3057. We get 0.1449 grams on top. We divide by 2.4506. Now we care about sig figs. Our top number has 4 sig figs. Our bottom number has 5 sig figs. So if we're calculating our percent error, our final answer should have 4 sig figs. That in turn gives us a value of 5.9128% that we in turn round to 4 sig figs, which would be 5.913%. Does this example make sense to everyone? Let me rewrite. There we go. Does this example make sense and how you have to follow the significant figure rules for each step sequentially?
Yeah, I do have a quick question though. So the bars on the side of 2.3057.
It just means absolute value, which means our percent error will always be a positive number.
Gotcha. Okay. And so like when we put that in the calculator, should we use the parentheses?
Yes. Yeah.
Okay. Thank you.
Professor, you said that was 5.913%?
Yes. Yep.
Thank you.
Yep, 5.913%. Any other questions I can address? So let's look at the next problem in the series. So in this case, we're asked to convert each of the following.
Oh, wait, why I get 0.059?
You need to multiply by 100%. Or multiply by 100.
100% is supposed to be 1, right?
So in this case, you're just multiplying by 100, but you put a percent at the end of your number to indicate that it's a percentage. So in your calculator, you just multiply by 100.
Okay.
Does that make sense? So like in your calculator, you'd enter it just like this. Does that make sense?
I need to think about it. I don't, but if you.
So essentially what you're doing is you're converting your decimal from this ratio into a percentage by multiplying by 100. Does that make sense?
Okay, yeah.
Perfect, perfect. Any other questions on this example? Okay, so let's keep going. And let's look at another unit conversion. Let's look at another unit conversion. This time we're asked to convert 2.75 milligrams per centiliter into micrograms per milliliter. So let's set up a solution map. So from milligrams to centiliter, our end goal is to go from milligrams to micrograms. So to do that, we're going to go through our unit of grams. Now we have centiliters on the bottom, and our goal is to get to milliliters. So then, what unit should we have as our intermediate? We're going to go from centiliter to what to milliliter? Yes, this is number 42. What intermediate unit are we going to go through?
Meter?
Yep, exactly right. Perfect. We always go through our base unit. So now that we have everything set up, what we're going to do now is we're going to execute on this problem-solving scheme. So first and foremost, we're starting off with 2.75 milligram per centiliter. To go from milligrams to grams, we know that there are 10 to the negative third gram per milligram. To go from gram to microgram, we know in 1 microgram, we have 10 to the negative 6 gram. Does this first series of unit conversions make sense? So in the end, we'd cancel and we'd end up with micrograms on top. Does that make sense to everyone? Does that look familiar?
Yes.
Okay. So now what we're going to do is we're going to convert from 1 over centiliter into 1 over mil. So to cancel our centiliters, we need to put centiliters on top and our desired units of liters on the bottom. And what power of 10 corresponds to centiliters? What power of 10 corresponds to centi? What does the centi prefix correspond to? What power of 10?
100?
10 to the negative second. So cent corresponds to 10 to the negative second. Does that make sense?
Yeah.
Perfect. Then we're going to go from 1 over liter to 1 over milliliter. And what does the milli prefix correspond to? What power of 10 does the milli prefix correspond to? What power of 10 does the milli prefix correspond to? Would anyone like to provide a proposal? What does the milli prefix correspond to?
Ten to the negative third?
Yep, exactly right. Corresponds to 10 to the negative third. Okay, perfect. So now that we have this set up, now what we're going to do is we're just going to execute on our unit conversion and plug in our powers of 10. So we have 2.75 times 10 to the negative third times 10 to the positive sixth times 10 to the positive second, because we're moving these negative powers of 10 up top, times 10 to the negative third. And our final units are microgram per milliliter. And that gives us a final value of 2.75 times 10 to the second microgram per mil. In other words, 275 microgram per mil. Does that make sense to everyone? Does this example make sense?
Yes.
Any questions I can address? So let's keep going on this example if we don't have any other questions. So for question 43, I'm just going to open up the table for question 43. So for question 43, we're asked to draw the Lewis structure and assess the molecular geometry for a range of compounds. So let's start on that. So let's look first at CClF3. So first we're asked to draw a Lewis structure. In the next question 43, identify the molecular geometry, the bond angles, and then identify whether the molecule itself is polar. Okay, so let's execute on that assignment. So first and foremost, we need to count our electrons. Carbon contributes 4 electrons, chlorine contributes 7 electrons, and fluorine contributes 7 electrons, and we have 3 fluorines. That gives us 32 electrons in total. We put carbon in the center and we surround it with our other 4 atoms. We form 1 bond each as we're constructing our Lewis structure, and then we fill in our lone pairs. So we formed 1 bond each, we're down to 24 electrons, and then we fill in our lone pairs until we run out of electrons or the octet rule is fulfilled on all of our atoms. So we burned through all of our electrons, and now looking at this structure. Looking at this structure, if we have 4 bonded atoms, so if we have 4 bonded atoms, what geometry occurs when we have 4 bonded atoms?
Tetrahedral.
Tetrahedral, exactly right. So this is a tetrahedral molecular geometry, because not only do we have 4 bonded atoms, we have 0 lone pairs. Now, my last question to all of you, is this molecule polar? So this molecule clearly has polar bonds, right? Are all of the atoms bonded to the central atom the same, or are they different? Do our dipoles cancel, or is there a net dipole in this molecule?
Don't know.
So thinking about our criteria, if we look at each of our dipoles, if the molecule is symmetrical, if the central atom has 0 lone pairs and all of the atoms bonded to the central atom are the same, then the molecule is nonpolar. Otherwise, the molecule is polar, as the dipoles do not cancel. So looking at this molecule, are all of the atoms bonded to the central atom the same or different?
Different.
Different. And since the dipoles are different, they don't cancel out completely, and as a result, this molecule is polar.
But I think last time you said if no, okay, never mind.
If there are no lone pairs and the atoms bonded to the central atom are all the same, because if the atoms are different, the dipoles are different and they don't cancel out. Does that make sense?
Yes.
Perfect, perfect. So one last thing, what would the bond angle be in this molecule? What would the bond angle be roughly for a tetrahedral geometry?
109.
Yep, 109.5 degrees. Yep, perfect. Does this example make sense?
Yeah.
Perfect, perfect.
So, Professor, when we turn this in, are we just pretty much taking a picture of our drawing, or are you asking us to circle?
There's a sheet that has blanks that you'll fill in, and that's why I recommend downloading that sheet there.
Gotcha. Okay.
This is just so that way you get an overview of what you're expected to do, but I have the sheet available, and that's what you'd fill in.
Okay. Thank you.
Let's look at the next example on the sheet, which is CH3OCH3. Okay. Okay, so let's count our electrons. Carbon contributes 4 electrons, and we have 2 carbons. Hydrogen contributes 1 electron, and we have 6 hydrogens. And oxygen contributes 6 electrons. Adding this up, we have 8 plus 12, which gives us 20 electrons. Okay, we're going to put carbon, oxygen, and carbon as our central atom, and we're going to surround them with hydrogens to fill out their octet. We're then going to form 1 bond each. 2, 4, 6, 8, 10, 12, 14, 16. We used up 16 electrons. We have 4 electrons remaining. Where do our last 4 electrons go? To complete oxygen. Exactly right. So now that we have this structure complete, let's look at each of our central atoms. So looking at this carbon, if we have 4 bonded atoms, what would the geometry be on this carbon?
Tetrahedral.
Tetrahedral. Okay, so we have bond angles of 109.5. So both of our carbons are tetrahedral. What about the oxygen with 2 atoms and 2 lone pairs? What do we call that geometry? 2 atoms, 2 lone pairs.
Tetrahedral bent.
Bent. So you just say bent. Yeah. And what bond angle does a bent geometry have? What's the bond angle for a bent geometry?
$120 degrees.
For bent
Oh, I'm
variants,
sorry, 109.5 degrees.
and it's actually a little bit less. It's about 105.5 because the lone pairs reduce our bond angle because they push our bonding electrons closer together as our lone pairs repel our bonding electrons.
Right.
Does that make sense? Does that sound familiar?
Can we write it's less than 109?
Yes, because for each lone pair, your bond angle gets smaller by about 1.5 degrees.
So, Professor, where it says 4 atoms and then underneath it says tetrahedral, are you pointing at that there's 4 bonds?
There are 4 atoms bonded to each of our carbons, and so each of our carbons has a tetrahedral geometry.
Ah, okay, thank you.
So the carbons each have the same geometry. So my question now, looking at this molecule, is this molecule polar? Does our central atom have polar bonds, and does our central atom have lone pairs?
Is this one have a 3 central or is it 2 central atoms?
Yep, it has multiple central atoms. So let's look at each of them. So looking at our central atoms, so we have polar bonds, right? And are the atoms attached to our central atoms all the same?
No.
They're all different, and our central oxygen has lone pairs. So overall, our dipoles don't cancel, and as a result, is this molecule polar or non-polar?
Polar.
Polar, exactly right.
So in this one, which are the central atoms?
There are three: carbon, oxygen, and carbon. And
Okay.
you look at each of them individually.
Professor, I'm a little bit confused on, so I get that if it has lone pairs,
If the
it's
central
polar.
atom has lone pairs and polar bonds attached to our central atom, then that means that our bond dipoles are not arranged symmetrically, and as a result, the molecule is polar.
Ah, okay, gotcha, I see.
Does that make sense?
Yeah.
Perfect.
What's the sheet say? Atom number 1, number 2, atom number 3. What
It's essentially because we're assigning the geometry for each of our central atoms separately. And that's why for carbon, you'd say one of our carbons is tetrahedral, the other carbon is tetrahedral, and our oxygen is bent.
Oh,
Does that
gotcha.
make sense?
Yes.
Perfect. Perfect.
So Professor, I'm trying to click on it and it says that it's gonna take me away from my practice exam.
Just
You mentioned that if we get off.
If you right click it, you can open it in a new tab.
Oh, okay, cool. Awesome, thank you. Yep.
And even though it says it will take you away from it, it just opens up the download link.
Okay. Oh, I got a little nervous there.
Yep. No, don't worry. If you've been writing everything down, it's all okay. So let's look at the next one, N2O. So let's look at N2O. This one's a bit of an odd one. So nitrogen contributes 5 electrons, and we have 2 of them. So that gives us 10. Oxygen contributes 6 electrons. So that gives us 16 electrons total. We'll put our nitrogen in the center and surround it with a nitrogen and oxygen, and then we'll form 1 bond each, taking us to 12 electrons. We then add lone pairs to our external atoms until we run out of electrons. Now, is the octet rule fulfilled? Is the octet rule fulfilled?
No.
No. So we're going to take one of our lone pairs and form a bond, and another one of our lone pairs and form another double bond. Now, the octet rule is fulfilled, and this structure would be reasonable. However, we need to assign formal charges. Would someone like to tell me what is the formal charge on this nitrogen? So taking our group number minus our number of bonds minus our lone pair.
-3.
What was that?
-3.
The formal charge, if we take we take our group number minus the bonds, not the bonding electrons, just the bonds, and minus the lone pair electrons, we get a formal charge of +1. Not the ionization preference, but the formal charge of this bonded atom using our formal charge equation. Does that make sense?
Can you repeat again?
So formal charge is the group number minus the bonded atoms minus the lone pair electrons.
Okay, gotcha.
Yeah. That's why oxygen's formal charge in this case is 6 minus 2 bonds minus 4 lone pair electrons, or 0. And this leftmost nitrogen has a formal charge of -1 from 5 minus 2 minus 4, which gives us a formal charge of -1. Redrawing this structure, so we have the following structure for N2O. Looking at our central atom, we have 2 bonded atoms. So what would the geometry be on our central atom?
Linear.
Yep, exactly right. The geometry would be linear. And what bond angle does a linear geometry have?
180.
180 degrees. Yep. Does that make sense?
Why do we need to calculate the formal charge?
Because you need to clearly state the formal charge in your final Lewis structure. It's part of a complete Lewis structure.
Oh, so that -1 is that negative charge on nitrogen left?
Yes, exactly.
Oh, okay.
Yep, exactly right. Now that we have our geometry, my question to all of you, is this molecule polar? Are the atoms bonded to the central atom the same or different?
Non-polar.
And why do you say that?
Because the same atom connected to central one, and then no pairs.
Are nitrogen and oxygen the same?
Oh, different.
Different. So then, are the bond? This would be polar, exactly right, because our atoms bonded to the central atom are different. We're still working on number 43. We're working on the third structure in question 43. Does that make sense? Perfect. So that's the complete response for N2O. Let's move on now to the fourth structure, which is H2O2. So looking at H2O2, let's now try to draw a Lewis structure. So first things first, oxygen contributes 6 electrons, hydrogen contributes 1 electron, and we have 2 each. That in turn gives us 14 electrons total. So we place our 2 oxygens as our central atom, and we place 1 hydrogen each, and we form 1 bond each. That in turn uses up 8 electrons. Sorry, not 8, just 6. And we have 8 electrons remaining, and we place our remaining 8 electrons on oxygen. Now that we have this preliminary Lewis structure, what is the geometry around this oxygen with 2 bonded atoms and 2 lone pairs? What geometry? That would be the electron pair, but what is the molecular geometry? When we have 2 atoms and 2 lone pairs, it would be bent. So then, what would the bond angles be? What would the bond angle be?
Less than 105 point something.
105.5. And the bond angles and geometry are the same for both of our oxygens because they have the same number of bonded atoms and lone pair electrons. Does that make sense?
Yes.
Any questions? So now that we have our geometry, my question to all of you is, as we have bond dipoles, is this molecule polar?
Polar.
Yeah, it would be polar. And the reason for that is we have polar bonds, and the bonds are not arranged symmetrically because our central atoms are bonded to different atoms, and our central atoms contain lone pairs, which prevents the dipoles from canceling and being arranged in a way where they can cancel. Does this make sense for question 43?
So this one, 2 oxygens, they all considered as a central atom.
Yes, the 2 oxygens are each considered a central atom.
But this time, why don't we calculate the formal charge?
We can, but they're both 0. In this
How
case,
how do you know it's both zero without a calculation?
when you do enough of these problems, you'll begin to notice bonding patterns that have zero formal charge. And oxygen with 2 bonds and 2 lone pairs has a formal charge of 0 because 6 minus 2 minus 4 gives us a formal charge of 0.
So for us, should we like each time we need to like calculate the formal charge? So be sure.
Yes, just to be sure. Mhm. And you only need to state it if the formal charge is not 0.
So is that when we check our formal charge, is that checking if it's polar?
Formal charges are different than whether the molecule is polar. Formal charge is checking to whether any of our atoms have a negative or positive formal charge in our bonded structure. While
Oh.
polarity is concerned with, are the bonds polar and are the bonds arranged in a way where the dipoles can cancel or the dipoles line up to lead to a net molecular dipole?
Okay.
Does that make sense?
Yes, sir.
Perfect.
Professor, I missed the first 20 minutes of when you started this. Are we actually doing the actual practice exam?
Yes, we're going over the questions on the practice exam.
Okay, I was just a little lost because I'm just writing everything down. I didn't know exactly what we were doing, so.
Yeah, we were going over each of the question numbers in the practice exam.
Okay, thank
Does
you.
that make sense?
Yes, we are on 44.
We're on 40, we just finished 43 and now we're doing 44.
Okay, got it. Thank you.
Perfect. So on that note, let's work on question 44, which is an electron configuration question. So we're asked to write the electron configuration for calcium. Okay, so how many electrons does calcium have? How many electrons does calcium have? What is calcium's atomic number?
20.
20, okay?
20.
So we're gonna fill our orbitals from the lowest to highest energy. So 1s2, 2s2, 2p6, 3s2, 3p6, and then 4s2. So we used up all of our 20 electrons. These outermost electrons, the electrons in the orbitals with the largest n value, are our valence electrons. So we have 2 valence electrons as our element. Calcium is in group 2A. Does that make sense to everyone? Does this electron configuration make sense for question 44?
Yep.
Perfect.
I write abbreviated one.
Yeah, and we're actually going to get to that. We're going to abbreviate each of these core electrons using the preceding noble gas, which would be, let me check the periodic table really quickly. The preceding noble gas, the noble gas immediately before calcium, is argon. So we'd abbreviate our core electrons as argon and write our valence electrons as 4s2. And this would be our complete abbreviated configuration. Does that make sense to everyone?
Yes.
Perfect. So now let's look at this next example.
Professor, can I ask a quick question
Yeah.
about the configuring electrons?
Yeah.
So as we're going through it, so passing it all up, 4s2, it would then go to 3d10 and then 4p6 and then
Yep.
5s2. Is that correct?
Yes, that's correct.
Okay, so then what's considered a a higher, I don't know how to say it, more,
Higher energy.
yeah, higher energy.
What is high? So the valence electrons, it's not just defined in terms of energy, but in terms of distance from the nucleus. And the electrons with the largest n value are farthest from the nucleus, most accessible, and thus they are considered the valence electrons. Does that make sense?
Yeah. Okay.
Perfect. So even though the 3D electrons are higher in energy than the 4s electrons, they're not considered valence since the 3D electrons are held closer to the nucleus.
Okay. Thank you.
Perfect.
What's the shell inner shell electrons?
Those are the electrons that are held closer to the nucleus compared to the valence electrons. So anything that's not valence electrons are considered inner shell electrons, as they're less accessible.
So we need to write those 1s, 2s, 2.
Not
Like
for the
the answer.
abbreviated. I'm just showing the longhand configuration before abbreviation.
You said you need to label the valence and the inner shell electrons.
Yep. So the 4s2, those are our valence electrons. While all of the electrons denoted by our noble gas electrons are considered our core electrons.
So core electron means the inner shell electrons.
Yep, exactly.
So when I write the answer, do I just write the argon as the core electrons?
Yep, or you can also call them inner shell.
Professor, so why wouldn't the 3s and 3p be called the core electrons?
They're also part of the core electrons. All of these electrons from 1s2 all the way to 3p6 are summarized and abbreviated using our noble gas core of argon. Does that make sense?
Okay. Yes, thank you.
Perfect.
So the answer that we type in, I'm sorry, I'm kind of confused. Is the AR4S2? Is that acceptable? I just put it in the chat.
That's more than okay.
Okay, and then so the inner, it's the same thing. The inner shell electron?
The inner shell electrons are abbreviated using the symbol for argon.
Oh, okay, got it. All right, thank you.
Any other questions on this example? If not, let's keep going. So for scandium 3+, so on question 45, so we know, for example, that scandium, what is the atomic number for scandium? What is the atomic number for
21.
21. Now, since we have a +3 charge, our number of electrons is equal to our number of protons, which is 21, minus our charge, which is +3, and that gives us 18 electrons. So then we first write out our longhand configuration.